if you remember a few lectures back, we did a design example based on the ZVTs, zero value time constant. We did a design example where we started with a common emitter. We said we needed a certain amount of gain and we wanted to maximize the bandwidth. And we saw that there was a progression of that design. We went from a common emitter to a cascade. And then from that, we added a buffer stage at the output, an emitter follower or source follower. And then from that point, we created some conceptual design, right? So that conceptual design can actually, so the conceptual design we had then was something like along the lines of this. So we had, it can be bipolar or MOSFET, doesn't matter. I'm showing it with bipolar because basically that's a little bit more general. So we had some V bias here, and then we had a buffer stage, a follower, with a, I believe we had a current source at the time, some I bias, and then driving a capacitive load in that case. And then we had an input that was connected to some sort of a source resistance R1, something like this. And I think this was like a 12 kilo ohm at the end of what we had. And the exact value doesn't matter really. We can pick any other value. And something like that. So we had this conceptual design and we were driving some sort of a capacitor CL. Now, and this was what we had. And we also saw that, we are losing some gain in the input voltage divider. We didn't really do that next stage, but next step, but we could actually add an extra buffer in the input to reduce that loss because we were losing some gain here. We didn't do this. So the next step would be in that design, if you wanted to enhance it, is say, okay, well, I can recover some of my gain here because I really don't need to have that. So let's get that conceptual design one step further and take it one step further. And then let's say you have also a follower here. Conceptually, that's driven by some R1 source resistance and Vn. So this is still a concept. I mean, yes, I mean, it has the right ingredients, but this is not a complete design, right? You can't go to stockroom and buy an ideal current source. And if you just connect it this way, that you have to think about the DC levels, making sure the transistor remain in the saturation, all those things. So now we can take this conceptual design and turn it into a real design. But there are different ways that we can do this. So we'll do it two different ways. I'll show you two different ways. One of them I just will show you, but one of them will go into the depth and details, which is either we are going to be taking this conceptual design and make it as a discrete design or as an integrated design. Now, that's kind of like a fork in the road in the way we will do this. And we want to kind of think about how we are going to be doing that. So let me ask you this question. If this were to be a discrete design, we'll do the discrete design, meaning that you're buying transistors and capacitors and inductors and making a printed circuit board, or I don't know, you make a breadboard or something like that, and you're putting it together on that. What are the primary parameters dictating the design choices? Well, in engineering, one of the primary parameters dictating everything is economics. Now, transistors are more expensive than capacitors and inductors in discrete transistors, right? So you don't want to add a whole bunch of transistors. You want to basically stick with these four if you don't have to add any more. So if you're turning this into a discrete design, what is it going to look like? Well, I'm going to have to bias these transistors properly. I have to make sure that, but I can use resistors and capacitors, and those things don't cost me much. So let's make that design. Let's turn it into something that you can actually put together and it will work or something like that, right? So let's say you're working off of a large power supply. Let's say you have a 12-volt power supply. So let's make the rail a plus 12 volt VCC. So this is the ground. And we want to make our circuit. So first we have to bias our transistors, right? So how do I bias that gain, the common emitter transistor, the one in the middle, lower transistor, right? So we have to bias it, right? So if we just apply a voltage to its emitter, it's going to be very sensitive. We talked about this in terms of biasing. So what do we need? we need to have a mechanism to stabilize the biasing of the transistor. So how can we stabilize the biasing? The bias of the transistor? Well, I need some resistor in the emitter, right? So we'll put some resistance that has to be, for it to have an effect, it has to be reasonably larger than Rm. Otherwise, it wouldn't have an effect. So let's say you put a resistor in the emitter, and then you connect your transistor here. Now, Rm, let's say we said 1 milliamp before. I think we talked about 1 milliamp, just typical. I mean, it doesn't matter. 1 milliamp is 25 ohms. So I make this 1 kilo ohm. A 1 kilo ohm resistor here. And then now this needs to be biased. So that means that if it's about 0.7 volts, if this voltage is 1 volt across this resistor, then I will get about 1 milliamp, right? I can control my current that way. So for this voltage to be around 1 volt, if this is a silicon transistor in that range of operation, this is going to be 0.7 volts, so this has to be at 1.7 volts. So let's say I use a branch, so I make this 1.7. So let's say I have another branch with 1 milliamp, so I make this 1.7 kilo ohm, right? And if I pass 1 milliamp through that branch, then it should provide me with the value that I need. Okay. So this 1.7 kilo ohm can also serve as that current source that I have for the, so I can put my follower here. So I can put my follower here and use this as the driving force for that. So this is 1 kilo ohm, 1.7 kilo ohm. Then I need to, of course, we need to generate the bias for the cascode, which we'll do in a second. Let's leave enough room here. And then, of course, you have your resistor, let's say 12 kilo ohm here. And then you need to also produce something that can, and so this is the input. Now, this base of this transistor, this needs to be biased also at some voltage, right? What voltage should I set it at? Do you have any thoughts on that? Well, if this voltage, I want this voltage to be 1 volt, right? Which means that I want this voltage to be 1.7 volts. Which means that in steady state operation, this voltage should be another 7.7 volts above that. So it should be at 2.4 volts. So voltage-wise, I want this to be 1 volt, DC-wise, 1.7 volts, and this should be at 2.4 volts. Right? So to get 2.4 volts, I need to make a voltage resistive divider, right, to get that value. I can make a resistive divider. So it's 12, let's say. So we can get a so 1.7, 1.4 volts, 2.4 volts. So let's say I want to make it out of a resistive divider that has a certain sum. So if I make this a 10 kilo ohm, let's say I put a 10 kilo ohm here, right? I want that to be 10 kilo ohms divided by the sum should be times 12 should be 2.4. So 10 divided by 10 plus that R at the top times 12 is going to be 2.4 volts. So that's going to be 2.4 divided by 12.2. 10 divided by 0.2, it's 50. So 50 has to be 10 plus R, which basically means R is 40K. Right? So this is going to be 1/5 division, which would be 2.4 volts, roughly. Right? So it produces the 2.4 volts that I want there. So that sets my bias point. But now I have to apply my source, and I'm running out of space. So here's my source. And then I have a source resistance, R1. Can I just connect this here like that? What happens if I do that? If I just take this and connect it like that, we short circuit that source to that input.
The input will get like overridden by the supply.
Right, because this from a DC, this is this is an AC source, right? Because from a DC perspective, this is a short. So this is shorting it DC-wise to ground. So all of this goes to nowhere, basically. This is going to turn off, this is going to turn off, nothing's going to turn on. So what do we do in a discrete design? One of the classic techniques in discrete design is basically put a coupling capacitor, right? C1. You have to pick a value. Let's just pick, I'm just going to pick a value and see how it turns out. 1 microfarad. Okay, we'll see what happens. So that's the coupling capacitor. So it allows me to establish this DC. This is really discrete design, right? This allows me to establish this DC level separately from that DC level. Okay, fine. So and then the same thing I have to. So and I have also an output, right? So I need to have a buffer. So I need to produce some sort of a current source here. Again, so I'm going to get rid of this calculation, and I have a follower. Now I don't have a current source. I have to put a resistor here. Now, what do I want this resistor to be? I want this current, again, for nominal operation to be at, so actually, no, this is, so this is the way I defined it. Okay, that's fine. This 12K is not good for 1 milliamp, obviously, right? Because then it will want to draw 12 volts. So my original assumption was that it's plus minus 12 volts. We can either do that or adjust this. Let's just make this negative 12 volts. So it's not 0, it's negative 12 volts. So it's something. The only thing that it would change is this division ratio, because now I have to divide the 24 volts and get 2.4. So I have to make this 5 to 40, or I can make it 10 to 80. Right? Would that work? No, not anymore? Okay, so what ratio do I need? I need 24 volts. I need 1/10. I need 10 to 90, right? Would be.
They should be pretty close together.
No, but this is so this is negative VCC plus that. So it should be 1 volt above the negative VCC, right? So this is whatever call it negative VCC. This should be negative VCC plus 1 volt, negative VCC plus that, negative VCC plus that. So it means that it needs to be 2.4 volts of the 24 volts, so it would be 1/10. So it should be 10 and 90 would work. So let's stay with this for now. Or we could have adjusted, keep this 0 and then adjusted that. Let's keep this. Now if that's the case, I want the output voltage, let's say, if it's drawing 1 milliamp, then nominally, if I'm drawing 1 milliamp out of 12 kilo ohms, it would be 12 volts below VCC. So this would be around 0, right? It would be halfway in between, negative 12 and positive 12. So this is another 0.7 drop. So this is going to be around 0.7, negative 0.7, this voltage. And then this is 12, so there's an 11.3 volts drop across this thing. So if I want it to be 1 milliamp, sorry, I will make this 11.7 kilo ohm. 11.3 actually, 11.3 kilo ohms. I mean, we can pick some other values that are not exact. I'm just like for now. And then we need to do something about this base, right? This base, we need to bias it. Where would we bias it? We don't want this to be too high, because think about it, you want this to have as much swing as possible. For it to swing high, not a problem. You cut the current, goes to 12 volts. For it to swing low, you have to make sure that after the drop that you have here and there, you get to a voltage that this does not go into saturation too early. So you have to pick a value for that value. And then you can do it any way you want, just like I picked a 10 and 85, so basically I'm going to keep it at a little bit above 2.4 volts, where this becomes basically 1.7. So this voltage is 1.7. This voltage is 1 volt. So this can go as initially, if the current was the same, if the current was 1 milliamp, this can go at down to 1.2 volts above this voltage, right? Because it's 1 volt here. But that will happen at a higher current for this to be pulled down that low. If, let's say, if this is to be pulled down all the way to negative 12 volts, the current has to be 2 milliamps. Right? If you're drawing 2 milliamps, there's 2 volts here, plus a 0.2, right? So this means that this guy can be the lowest is 2.2 volts above the minimum voltage. And I need another 0.2 for this guy before it goes to saturation, so 2.4. So it's kind of a similar breakdown, right? So I can use a similar resistive divider here. I'm just going to show it. Let's do it. So I can do a 90K, 10K here. Okay. And then, of course, let's say I have some load. Now, I can actually make it even it can be a capacitive load or resistive load, doesn't matter. Let's keep the capacitive load, doesn't. But some load. So this is the output, V out. So is everything okay? Is everything, would this have an amplification, proper amplification? What is the gain of this stage? We were shooting for a gain which was, I think, about 100 or something like that, if I'm not mistaken, right? Before. But what is the gain for this? What is the gain of this? This is the gain stage, right? This is the gain stage. Is there a problem? I mean, can you tell me roughly what the gain of this gain stage is now? You should be able to tell me approximately very quickly by looking at it. The total resistance in the collector to the total resistance in the emitter, 12 by 1. The gain is less than 12. It's not high. Why? Because I put that resistor there to stabilize my biasing, I killed my gain. So what do we do? What do we do to save that, to help that? Can you think of a solution? You're discrete. You're in discrete design. You can add capacitors, resistors, etc., etc. Can you fix this? Where do we care about this gain being high?
Can we replace the resistor with something that, like a reactive element that will have, it won't kill the gain in the...
Exactly. You need to use a reactive element. And what do you want it to do? Before we decide what the reactive element is, what do we want this element or this impedance that we are going to introduce here to do? We want it, from a DC perspective, still to be a resistor, because we want it to be stabilizing the bias, right, which is DC. But we want it from an AC perspective to be what? At the frequencies of interest, what do we want it to be ideally? What's the best thing to have here? Nothing, right? Short circuit. So what is the thing that I can add to this to make this a short circuit at the frequencies of interest, mid-band, but not affected at low frequencies? A capacitor in parallel, right? The reactive element is a capacitor. Let's call it C bypass, CB. Let's call it one. Let's make it 1 microfarad again, just as a starting point. And are we good now? Do we have gain? Are we good? There's something else that's still not properly done from an AC perspective. From an AC perspective, in our conceptual design, if you look at the conceptual design, this node is what? AC-wise? Ground. This is a fixed source. Are we grounding that node? No. What is the resistance from that node to ground? 10 kilo ohm parallel 90 kilo ohm. Right? So that's high. How do I make it? But I need those resistors to establish the DC level. So how do we make it, from an AC perspective, a ground? Another reactive element, right? What? What should I use? A cap to ground, a capacitor to ground. I don't know. Let's call this CC, CB, I don't know, CA. Let's make that 1 microfarad. Okay. So now we need to kind of, so now this can work. This is a legit design. We just picked some capacitors arbitrarily. So we want to make sure, we want to look at our low pass cutoff, low frequency, high pass cutoff, omega L, right? We want to estimate that. We know we've done a lot of estimates of omega H's, so we're not going to worry about that. These are the three capacitors that determine the omega L. How do we know? Because if you actually make them short circuit, the circuit becomes closer to what it should be. When you infinite value them, they are the ones that infinite value of them makes the circuit better. Makes it closer to the idealized circuit, to the conceptual design. Right? So we need to apply the infinite value time constant to these things. There are three time constants. Right? So let's calculate those time constants. So there's a tau A infinity, tau B infinity, and tau C infinity. Let's calculate them. So tau A infinity, what is it? Well, what is the resistance? So first of all, you have to infinite value everything else. So this is short-circuited, and this is short-circuited. So this short-circuiting it basically makes this a common emitter with no degeneration. Right? What is the resistance seen looking into here? In this case, they are not affecting each other really that much. But if they were, you have to think about it. What is the resistance seen by this capacitor? So it sees these parallel combinations plus what? Plus the input resistance seen into, in parallel, not plus, in parallel with this input resistance. What is that input resistance? R pi plus 1 plus beta times whatever you see looking into the emitter, in the emitter. Your emitter is basically just RO, because this is now shorted. So RO, let's say, I don't know, 100 kilo ohms, if VA is, if this is 1 milliamp and VA, the early voltage is 100 ohms, so that makes it 100 kilo. So that's going to be gigantic, right? Because it's times beta, so if beta is 100, this is going to be 10 mega ohms. When you go above a few mega ohms, it's meaningless numbers. This is infinity, meaning that other things will dominate. So don't get kind of hung up on, oh yeah, I made my resistor like 79 mega ohms, and like this is going to be a great circuit. No, it's not going to be a great circuit. Your leakage current is going to be more than that. It's going to kill it. Okay? So anyway, this is gigantic, right? We should not even worry about it. It's 10 kilo ohm parallel 90 kilo ohm, right? So it's 9 divided by 10 kilo ohms, so it's like basically 900 ohms. So that's 900 ohms times whatever we said, 1 microfarad times 900 ohms. So it's 900 microseconds, or 0.9 milliseconds. That's one time constant, one infinite value time constant. How about tau B? What is the resistance seen by CB? Well, for this calculation, you have the 1 kilo ohm, obviously, and you have the resistance seen looking into the emitter. What is it? Well, there's an alpha Rm there, plus whatever is in the base reflected into the emitter, right? Divided by beta. Beta plus 1, but it doesn't matter, right? So now I have to see what is the resistance looking this way. Well, the resistance looking this way is Rm of this guy plus whatever it sees in the base divided by beta. What does it see in the base? It sees this guy parallel this guy, and now remember, this is shorted. This is infinite value. Parallel this guy. So we said, I don't know, did we say this was 1 kilo ohm? If this was 1 kilo ohm, so it's 1 kilo ohm parallel 10 kilo ohm parallel 90 kilo ohm, it's 1 kilo ohm. So this is 1 kilo ohm. Therefore, looking up here, you will see 25 ohms, which is Rm, plus 1 kilo ohm divided by 10. Sorry, divided by 100, by beta. Beta plus 1 beta. 10 ohms. So that's 35 ohms. This is 35 ohms parallel 1.7 kilo ohms. It's 35 ohms. Right? Divided by another beta when you look through here. So that's 0.35 ohms plus 25 ohms. So it's nothing. It's the Rm, 25 ohms. I don't need to really worry about the 0.35 ohms. If you want to, you can just write 4 significant digits, but it's completely meaningless. Completely meaningless if you do that. Okay? But, so it's 25 ohms. Parallel 1 kilo ohm, it's still 25 ohms. So it's Rm. We know it's Rm. We had to check it, right? to make sure that we are not making wrong assumptions. Okay, so it's 25 ohms parallel 1 times 1 microfarad. So it's 1 microfarad times 25 ohms. So that gives me 25 microseconds, or 0.01 milliseconds. And then tau c, this guy, what's the resistance seen by this guy when everything else is infinite valued? If this is infinite valued, this is shorted, so this is going to be r pi. Now this matters, right? Think about it. Now we have to short this because we have to get the r pi from here. So this is going to be 2.5 kilo ohms because this is not there, right? So so this matters now. 2.5 kilo ohms parallel 1.7 kilo ohms. So looking into the combination of these two, it's 1.7 parallel 2.5. So it's 1.7 times 2.5 divided by 1.7 plus 2.5. It's 1. So this is 1 kilo ohm. Okay? What do you see looking into here then? You see that times beta, this becomes 100 kilo ohms. So now it doesn't matter because 100 kilo ohms parallel 10 kilo ohm and 90 kilo ohm is basically 10 kilo ohms. So you see 10 kilo ohms this way, and you see 1 kilo ohm that way. So you see 11 kilo ohms, roughly. So that basically brings you to 1 microfarad times 11 kilo ohms. 11 kilo ohms, yeah. So that's basically 11 milliseconds. Large time constant. So what's my estimate of the bandwidth of the low cutoff, omega L? Is the sum of the reciprocal of these time constants, right? So which one matters? Which one is dominating, really? Tau b infinity. This one is limiting me now. I don't even need to calculate the other ones to just get an estimate. So what is the estimate? So it's 25 microseconds, right? 25 microseconds. 1 over that divided by 2 pi. 1 divided by that. So that's 100 times 2 times pi. It's 6 point. So this corresponds to, so if I assume that it's 1 over, simply 1 over tau b infinity, if it's dominated by that, it's the sum, but here I'm just making a big approximation, just based on this, let's say omega h prime, based on that, is going to be 6.4, 2 pi times 6.42 pi times 6.4 kilohertz. So this is not a good audio amplifier because a lot of audio happens below 6.4 kilohertz. In fact, most of the audio energy. Yes? Is that omega H or omega L? Omega L, sorry. Yeah, this should be omega L. Thank you. And omega L approximation, the total approximation is the sum of these infinite value time constants. In this case, there are 3, but in general to n. Right? So this is not good because that by itself is messing me up. So I need to do what? This capacitor needs to be what? Bigger. How much bigger? If I want to go from 6 kilohertz to, let's say, 60 hertz, it had to be 100 times larger. If I want to go to 20 hertz, it has to be 300 times larger. So I'll make this like, you can make it a big capacitor, right? So I'll make it a, I don't know, 500 microfarads. If you make this one 500 microfarads, what's going to happen? So that's going to multiply by 500. So you get 12.5 milliseconds. So then this is going to be modified to, so this is like 500 microfarads times 25 ohm. And the reason for this capacitor being important, you see all 3 capacitors are the same size, were the same size originally, is that the resistance seen here is very small. So this is the exact opposite of zero value time constant. Places where you have high resistance, low resistance are important here, are limiting. You remember the high impedance nodes were the problem for the high cutoff frequency? Now the low impedance nodes are the problem for the cutoff frequency here. So anyway, so that becomes whatever, 12.5 milliseconds. So if that's 12.5 milliseconds, this is 11 milliseconds, then this is going to be dominating. Right? So now I can estimate my bandwidth based on that. So I can calculate what the reciprocal of that is. The reciprocal of that corresponds to
Should that would have been 900 ohms or 9 kiloohms?
sorry, which one?
I thought it was a 10K parallel to a 9
Yeah, it should be 9. Yeah, you're right, actually. This is 9 kiloohms. This should have been 9 kiloohms. Oh, no, yes, it should have been 9 kiloohms, sorry, yes. So this becomes 9,000, or it becomes 9 milliseconds. Let's make that correction. So now they're on the same order, so you can actually approximate it. So the reciprocal of this thing, so you can calculate the sum of the reciprocals. So you can calculate the sum of the reciprocals, so you have 1 over 0.09 plus 1 over 12.5 plus 1 over 11 milliseconds. So that becomes, for the sum, the new modified sums, is going to be 282 radians per second. And you can get that and divide that by 2 pi. And you get basically, so it becomes 2 pi times 45 hertz. Now, if you're not making the audio amplifier for everything, this may be okay. If you want to push it down, it means that you need to scale. So you can see all 3 of the time constants are on the same scale now, right? So basically it means that you need to make all of the capacitors probably 3 times as much larger. And then you will get a cutoff frequency about whatever it is, less than 20 kilohertz. Okay, so you can see what's happening with the infinite value time constant. You can estimate this bandwidth. So this was a pathway for discrete design, right? So how about an integrated design? If I went kind of like, let's go back to our conceptual design and say now I wanted to implement this concept as an IC in an integrated circuit. What would we do? I mean, we're not going to do analysis. We're just going to draw it. We're going to sketch the design, but because we've done the analysis before. So how would you do that? How would it look like? Now, what is the trade-off? The trade-off is very different, right? Oh, but and what happens is that the trade-off here is that the number of the transistors are free, practically, incrementally free. The capacitors are expensive, right? And resistors are expensive. Capacitors are even more expensive. So how do we do that? How do we design this? How do we go about this design? But on integrated circuits, we can also do something which is useful. On integrated circuits, we can actually, what is one of the realization or one of the, I guess, manifestations of a common emitter on an integrated circuit in an IC configuration? It's differential pair. Right? Differential, if you think about a differential pair, the half-circuit equivalent of a standard differential pair is a common emitter. So we can implement it as a differential circuit. So the way we implement it as a differential circuit, if we take this circuit and we wanted to design it as an integrated one, so we could have 2 followers. Now we can have current sources, right? Current sources are not a problem. So you can have actually a differential input. You can have 2 current sources. Now, current sources we know how to make. We can actually turn them into a real current source, or not. And then you can bring this input to a differential pair. So you form a differential pair. So these 2 are representation of that guy. You need another current source here. This goes to the input. You need to make it into a cascade. You make that differential. We need to generate this bias current, bias voltage. We can do it in various ways. You can have the resistive loads. Then you go to another buffer, which is also differential, so it's doubled. And then there's a current source here and a current source here, and this is your differential output. This is one rendition, if you will, of a differential, an integrated circuit rendition of this thing. If these resistors bother you even, you can actually replace them with active loads. You can put current sources there. Right? So for example, these could be, if you have PNPs, if you have decent PNPs, or if not, you can use other things. You can do this. So these are basically current sources. You can replace these current sources. We actually put actual transistors to represent these current sources. And then you need probably some sort of a reference branch. You can have some sort of a fancy current source. What I'm drawing is a little bit, okay, let me draw it properly. You probably need another reference branch to come and feed the reference branch here. These are your inputs. And you need to generate this bias current. You can do it with some sort of you want to reference it, for example, to this voltage. You can have a little current source, an extra current source here, feeding some sort of a resistor. Or you can have like a diode connected transistors, if you will, or one, depending on how you want to do it. Here, and you want to, of course, this needs to be a scale, so this current doesn't steal all of that current. It needs to be a smaller fraction of that current, and something like that. So that conceptual design in an IC becomes that. And contrast it with this. At some level, they're the same. They're both this. But the economics of it and the way you implement it, and that those trade-offs completely change them from one to the other. Does it make sense? Any questions? All right.